Our project is design of RISC-based 32-bit MIPS processor with 5-stage pipelining for hazard detection. The objective of this project is to design a 5-stage pipelined MIPS processor using Verilog HDL code and to synthesize it using the Vivado Xilinx compiler. Basically, MIPS is a microprocessor without interlocked pipeline stages. By designing MIPS, we are basically also designing a RISC-based CPU. In MIPS, it includes 5 pipeline stages, which are instruction fetch, instruction decode, execute, memory, and write back stages. The instruction set being used here is 32-bit. MIPS-based RISC processor is a pipeline architecture implementation. Pipeline is nothing but it is a process that applies uh, a parallel work, which means if executing single instruction simultaneously, it improves the throughput significantly. Our idea is to improve the speed of the processor and to give higher performance and higher throughput and to reduce the time period of the processor. And this is the existing work already done. In this existing work, due to the single instruction set, the hazard occurs. Basically, particularly data hazard occurs, and in our proposed work, we proposed a design to identify the data hazard, and the software used is Xilinx Vivado and model simulations. Single cycle implementation. In the existing work, they used a single cycle implementation. In this, all operations take equal amount of time. There are many instructions in CPU. Each instruction might take different amount of time, but in case of single cycle implementation, all the operations take equal amount of time, which is completely in a clock cycle. But in clock cycle, it is determined by the time taken by slowest instruction. Usually the slowest instruction is load word. And this is the block diagram of the single cycle instruction. Our proposed work is multi-cycle data path. Comparing to the existing work, in our proposed work, we additionally add some mux and some register parts here. In multi-cycle CPU, it consists of many processes. If one process is taking place, instead of waiting for that process to complete, we can simultaneously start a new process, which is nothing but a pipelining process. It can also be called as parallel processing. Each part of the process is divided into various pipeline stages. So for every clock, the process is stored into next pipelining stages, enabling another operation to start in that stages without disturbing the previous stage. Hence, all the stages in the implementation can be used simultaneously. This can also increase the throughput of the design. There are 5 stages of MIPS. In the instruction fetch. Instruction fetch is used to fetch the instruction from the instruction memory, and it is stored in the instruction register. The stage has various modules like instruction memory, which holds the instruction need. The instruction readout from instruction memory are stored in instruction register, which is a part of instruction fetch and instruction decode stage. This is the block diagram of instruction fetch. Instruction decode. This stage decodes the instruction sent from instruction register. It reads the operand required for a register file. The register module gives out the value of 2 registers, register A and register B, which are sent to ALU through the instruction decode and the execution stages. And execute stage. In the 5 stages of MIPS processing, all the instructions which are received from the instruction fetch and instruction decode stages are being executed in this stage only. All operations like functional, logical, binary operations take place in this stage. This stage also has left shift and an adder. The result from ALU is sent to ALU output register, which is in memory stage. Memory stage basically has a data memory. It is of 64 word deep. This register is in memory or a write back stage. Write back stage is nothing but it usually writes back the result into a register file. Pipelining, main content of a project is coming here. In pipeline is nothing but doing one or more operation at the same time in a single data path. A multiple CPU consists of many processes. If one process is taking place, instead of waiting for the process, we can simultaneously slot a new process without disturbing the previous one. Hence, all the stages in the pipeline path can be used simultaneously. Pipeline stall is a delay in execution of an instruction in order to resolve a hazard. In a standard 5-stage pipeline, during the decode stage, the control unit will determine if the decode instruction reads from a register. If this condition holds, the control unit will stall the instruction by one clock cycle. Due to this, we can resolve the hazard. And this is the concept of stalling. The following is a 2 execution of the same 4 instruction through a 4-stage pipeline, but a delay in fetching of the purple instruction in cycle 2 leads to a bubble being created, delaying all the instruction as it will. And this is the sample code. Now we are running the project. First we need to open the code, and it will open the code and give the synthesis to and give click on synthesis, and further we need to give run synthesis. It will run like this. By clicking on synthesis, we can be able to see the synthesized design of the code what we have given. We can be able to see the commands while initializing in the TCL console or in the design runs, which is present at the second part of the software. It shows synthesize complete. Now we can be able to see the synthesized design. Since there is no errors, the synthesized design is visible here. It has 8 ports: dy3, x1y3, x0y2, x1y2, x0y1, x1y1, then dy0 and x1y0. This is actually what it looks like, the device. Then now we need to run the simulation. Now we need to run the simulation. For that, in simulation tab, click on run simulation, then click run behavioral simulation. It starts simulating. If there is any error in the code, we can see that in the TCL console it shows the every command line. If there present any error, it stops compiling and it shows an error message. There are multiple steps present in executing the simulation stage. At each stage it shows the command message in the TCL console. Now the synthesize complete for the RTL schematic diagram. These are the modules present in our code, which is nothing but each blocks like ALU and five MIPS pipeline stages like instruction fetch, instruction decode, memory and write back units. Now we can see the op codes present in our code, and these are the units: memory to register and memory write back, register write. This represents the values and their memory locations. And this is the schematic diagram we are obtained by executing the code. In this it represents multiple blocks here. The each block represents each stage, like instruction fetch, instruction decode, then execute stage, then memory stage, and write back stage. The presents adder and the multiplexers and the arithmetic logic units. This schematic diagram, by using this schematic diagram, we can be able to obtain the final output of the code. Now the final output of the code we can get in this window. We can view each stage output by clicking on that stage, which is visible at the left side of the window, like ALU output, ALU execute, and control signals. At each stage we can see the output of that particular stage. If any error occurs, we can modify the code at that stage and then run it again. At the top it represents the time period taken to execute that stage, like a 164 nanoseconds. Here we can given the input data as 1, we need to add 1 and 2, and the output data will be 3, which is stored at T2. 1 plus 2 is 3, which is stored at T2. For executing this, it took 610 nanoseconds. This is the MIPS assembly code. The first step instructs add T0 and T1 and store it in T2. This is the X code, which is obtained from an online tool by running the MIPS assembly code. This is the output waveform of the X code, which we have already seen. And this is the register file before execution of the code. Like what like this is like input side, and the data memory before execution, the memory location of the inputs. This is register file after execution, like storing the output values, and the data memory after execution code is the memory location of the output values. All the values stored in an array, stored like an array way. After executing and running all the stages, the CPU time takes 7 millisecond and the elapsed time is 8 millisecond. Total it took 15.5 millisecond, and the average time is 3.1 millisecond, whereas in a single cycle implementation the average time is 9.69 seconds, but here we get 3.1 milliseconds only. Thus pipeline architecture is nearly 3.467 times faster than the conventional single cycle implementation. In such case, CSIC architecture CPU of same standards of area and frequency, average time per instruction is around 2.5 to 7 microseconds. Thus, RISC architecture can be considered to be relatively faster than CISC architecture. In future we can identify various hazards like control hazards, um, and we can use cache memory in place of a single memory. Also we can complete the ASIC flow design and to complete the full physical design.